Have you ever just, looked up at the night sky and felt that sense of, wow?
Oh, absolutely.
Maybe you've heard the buzz about this comet that's coming. C 2023 A3. Tsuchinshan 8TLS, discovered back in February 23.
Right, it's heading our way. A real celestial guest.
And it kind of makes you want to really see it, Prepare yourself.
And the amazing thing is you don't always need some giant observatory. The surprising truth, you've already got one of nature's best astronomical tools.
You mean my eyes?
Exactly. Your own eyes. They're like, well, they're basically the telescope you were born with. Got all the key parts, like a modern camera system.
That's a cool way to think about it. It makes sense. For so many people, that spark, that love for space, it starts simple.
Yeah.
Maybe just looking up, like me. Or I read about professional astronomers getting hooked by a cheap, basic telescope.
Or even like Andrew Huberman, the neuroscientist. He talks about how an aquarium full of fish just kicked off his love for science. Simple things.
Right. So our mission today, in this deep dive, is kind of tap into that wonder. Show you how to unlock the universe with what you've already got.
That's the plan. We're going to take a tour of your eye, see how it stacks up against a sophisticated telescope, the similarities, the differences.
How it works, what it can do. Its limits, too, I guess.
Definitely its limits.
Yeah.
But also, crucially, how you can actually optimize your vision. Make it better for looking at the stars, just like the pros do.
And we'll connect it back right to the history. Galileo, James Webb.
Absolutely. From Galileo looking up for the first time, really, to the JWST blowing our minds today. It's all connected.
Okay, let's do it. So this natural telescope, how does it even start to work? Where does the light first go?
Okay, so optically speaking, the first stop is the cornea, that clear outer layer.
Right.
It's not just a window, though. It's actually the eye's main lens. It does most of the focusing before light even gets inside properly.
Huh. I didn't realize it did most of the focusing.
Yeah, it's powerful. And that's actually what they reshape in LSIC surgery,
Yeah.
using those incredibly precise lasers. Some of that tech comes from Nobel Prize-winning work on ultra-high pulse lasers, by the way. Donna Strickland.
Wow. Okay, so cornea handles the first focus, but how does it control how much light gets in? Like the aperture setting on a camera.
Ah, good question. That's the job of the iris, the colored part of your eye.
The pretty part.
Exactly. It controls the size of the pupil, which is the actual hole light goes through. Think of it like an automatic aperture.
Automatic.
Yeah, it adjusts constantly, dynamically, based on the light. That's a big difference from a telescope or a camera, where you usually have to set that manually, right, for the dynamic range. Your eye just does it.
Instantly. Okay, that's pretty smart. What's next, after the iris and pupil?
Then you hit the lens. Now, this isn't like the hard glass lens in a telescope.
No.
No, it's pliable, squishy almost, biological tissue. Tiny muscles pull on it to change its shape.
To fine-tune the focus.
Exactly, to focus the light perfectly onto the retina at the back. And, speaking of the squishy bits, most of the eye is filled with this gel.
Yeah.
The vitreous humor.
Vitreous humor. Sounds funny.
Yeah, nothing humorous about it, really.
Yeah.
Just reminds me of that old eye doctor joke.
Oh.
What's the difference between an ophthalmologist and an optometrist?
I don't know.
About 150 grand a year.
Okay. But jokes aside, that lens focuses the light onto the retina. That's the detector.
That's the detector. The retina is the CCD camera of your eye, you could say.
Yeah.
It's incredibly sensitive to light, even really faint light.
And this is where it gets weird, right? The brain connection.
This is where it gets really mind-bending. Andrew Huberman makes this point all the time. The retina, it's the only part of your actual brain that's not inside your skull.
Wait, seriously?
Seriously, it's brain tissue, right there in your eyeball.
Yeah.
Connected by the optic nerve.
Wow.
Which, funnily enough, the optic nerve connection is also what creates your blind spot. Little patch where there are no detectors.
So your brain literally extends into your eye. That's wild. Okay, so the light hits this brain bit, the retina. Does the image appear right side up?
Ah, no. That's another similarity with many telescopes, actually. A single lens, or like most refractor telescopes with two lenses, flips the image.
So we see everything upside down initially.
On the retina, yes. But your brain, being the amazing processor it is, just flips it back instantly.
Yeah.
You never even notice.
That's incredible.
Though, some telescope designs, reflectors, or certain refractors can give you a right-side-up image directly.
Okay, so let's recap the analogies. Telescope lens is like the eye's lens.
On cornea.
Right. The telescope aperture control is like the iris controlling the pupil, and the camera detector, the CCD, is like our retina.
Exactly. But always remember, the eye is alive. It's adaptable biological tissue, not just silicon and glass.
Right, a living camera. And the sensitivity, you said it's amazing.
It really is. Inside the retina, you've got two main types of light detectors, photoreceptors, rods and cones.
Rods and cones, okay.
Rods are, like the ancient ones, super sensitive, great in dim light, think lizard-like night vision. Cones are less sensitive, but they give us color. C for cone, C for color. Easy way to remember.
Okay. Rods for low light, cones for color. How sensitive are we talking?
Get this.
Nah.
Studies published in top journals like Nature have shown the human eye in a perfectly dark room can actually detect a single photon of light.
One photon, seriously.
One single photon. It's almost unbelievable sensitivity.
But there are downsides too, right, compared to a telescope?
Yeah, definitely. Like telescopes with lenses refracting telescopes, our eyes suffer from something called chromatic aberration.
Chromatic, like color.
Exactly. Different colors, different wavelengths of light don't bend quite the same amounts. They don't all focus perfectly at the same spot. It can create a slight blur or color fringing.
Ah, okay. Do reflecting telescopes have that problem?
Nope. Because they use mirrors, not lenses, to focus light, they completely avoid chromatic aberration. It's one of their big advantages.
And color vision itself. How do telescopes see color compared to us?
Well, telescopes usually need filters. They take separate pictures through a red filter, a green filter, and a blue filter.
Like separate exposures.
Often, yeah. Or sometimes they have different colored pixels. Either way, you have to combine those images later to make a color picture. And it can sometimes cost you a little bit in sharpness and resolution.
Whereas our eyes
process color instantly all at once, thanks to those cone cells. It's seamless.
Okay, so sensitivity is incredible, color is instant. But what about the eye's other advantages? Things telescopes can't do.
Oh, a huge one is the field of view. Your eyes together give you something like 150 degrees of vision.
150 degrees? That's huge!
It's massive. Compare that to, say, the Hubble Space Telescope. Its view is tiny, a minuscule patch of sky. Even a decent amateur telescope might only show you a few degrees at most.
Why do we need such a wide view?
Think evolution. For early humans, that wide field of view meant crucial situational awareness. Spotting predators, finding food, navigating. Survival, basically.
Makes sense. And that ties into peripheral vision, right? Which astronomers actually use.
Exactly. It leads to that trick called averted vision, which we'll definitely get into. It's about using those super-sensitive rod cells, which are more concentrated in your peripheral vision.
Cool. Any other weird eye superpowers?
Well, there's another property of light. Polarization. Most people aren't aware of it, but some people can actually perceive polarized light.
Perceive it? How?
It's a faint effect called Heydinger's brush. On a plain blue sky or a white screen, some people can see a sort of yellowish bow tie or propeller shape.
Yes.
Subtle.
What causes that?
It's linked to pigments in the macula, the central part of your retina. Little filters, basically xanthophylls, lutein. And doctors actually use its presence or absence sometimes to check for things like macular degeneration.
Wow. Okay, so the eye's got some tricks. But where do telescopes really, pull ahead, technology-wise?
Well, size is a big one. For really faint objects, you need to collect a lot of light, which means a big mirror or lens. Reflecting telescopes, the ones Isaac Newton pioneered back in the 1700s, can be made much larger than refractors.
How big are we talking?
Refractors, the lens-based ones, kind of max out around a meter across. But reflectors, we're building telescopes with mirrors tens of meters across now. Like the ones at the Simons Observatory in Chile. Huge instruments gathering incredible amounts of light.
Okay, size matters. But what about seeing clearly? Stars twinkle, right? The atmosphere messes things up.
Yes, the twinkle, atmospheric turbulence. That's where one of the most brilliant modern technologies comes in. Adaptive optics.
Adaptive optics sounds fancy.
It is fancy. Modern reflecting telescopes use these incredible deformable mirrors. Claire Max at UC was a key pioneer here. These mirrors can change their shape hundreds, even thousands of times a second.
Change their shape? Why?
To counteract the atmospheric blurring in real time. They often create an artificial guide star high up in the atmosphere using a laser.
A laser guide star?
Yeah, they shine a powerful laser up, usually yellow, to excite sodium atoms way up there, making them glow. They know exactly what that star should look like, a perfect point. By measuring how the atmosphere distorts that artificial star, they can tell the deformable mirror exactly how to bend and flex to cancel out the distortion for the actual starlight.
So they're basically untwinkling the stars.
That's a perfect way to put it. It allows ground-based telescopes to get images almost as sharp as space telescopes sometimes.
Yeah.
And interestingly, the tech has roots in military applications, like keeping sniper scopes steady.
That is absolutely mind-blowing. Okay, so given our eyes are these amazing, if limited, instruments, how can we, the listeners, optimize our own vision? How can we squeeze every last photon out of the sky?
Okay, one of the most fundamental techniques, especially for faint objects, is averted vision.
Averted vision, looking away.
Exactly. You don't look directly at the faint fuzzy thing you're trying to see. You look slightly off to the side.
Why does that work?
Because you're shifting the object's image off your central vision, the fovea, which is packed with color-sensitive cones but not great in low light. You're moving it onto the part of your retina that has more of those super-sensitive rod cells.
Ah, using the night vision cells.
Precisely. It takes practice. You kind of have to learn where your peripheral vision is most sensitive, but it can make a huge difference. Suddenly, faint galaxies or nebulae just pop into view.
Cool trick. What else is essential for good stargazing eyes?
Dark adaptation. This one is absolutely key, and people often underestimate it.
Getting used to the dark.
Right. But it takes time. Real, full, dark adaptation takes about 30 minutes. Maybe even longer for some people.
30 minutes.
Yep. That's why serious astronomers are religious about avoiding bright lights. No checking your phone, no white flashlights, red light only, because it affects your night vision less.
And why looking for faint stuff during a full moon is so hard.
Exactly. The moonlight just washes everything out and prevents your eyes from reaching maximum sensitivity.
Okay, dark adaptation, averted vision. What about, physical stuff? Our bodies.
Oh yeah, that matters too. Think about oxygen.
Oxygen.
Yeah. Why do they build observatories on high mountains like Simon's at 17,000 feet? Partly for clearer air, less atmosphere, but maybe also because higher altitude acclimatization improves vision slightly. Even at sea level, some amateurs swear by taking deep breaths, really oxygenating their blood before observing. Some even use those little boost oxygen canisters.
Stacy, does that work?
Anecdotally, some find it gives a noticeable edge, especially for faint objects. More oxygen to the retina seems to enhance sensitivity. Worth experimenting with deep breathing anyway.
Huh. And just general health.
Absolutely critical. Good cardiovascular health means good blood flow. Your eyes have tiny, delicate blood vessels. They need that steady supply to function at their peak. So yeah, fitness matters for stargazing.
Which brings up the flip side. What should we avoid? What lifestyle things mess up our night vision?
Okay, this is important. Alcohol is a big one. Even just one glass of wine can noticeably impair your night vision sensitivity.
Really? Just one glass?
Yeah, the studies show it. Caffeine, well, it keeps you awake, but it can also make your eyes and your hands, if you're using a telescope, a bit jittery. Not great for steady viewing.
Okay, so less coffee maybe.
And nicotine, smoking, double whammy. The smoke itself can get in your line of sight, obviously, but nicotine is a vasoconstrictor.
Meaning?
It tightens your blood vessels, restricts that crucial blood flow to the eyes that you want to maximize. So definitely avoid smoking while observing.
Good advice. Okay, let's shift gears a bit and connect this amazing eye science back to history. To Galileo.
Galileo. His story is fantastic. He didn't invent the telescope, but he dramatically improved it and, crucially, knew where to point it.
But he first used it for military stuff.
That's right. His first big demonstration was for the Venetian Senate. He showed them how his improved telescope could spot enemy ships maybe 3 days earlier than they could with the naked eye.
Smart move.
Very smart. It basically guaranteed him his job, his tenure, and got him a big raise in his startup funding, essentially.
But then he turned it upwards.
Then he turned it to the heavens, and everything changed. He saw the moon wasn't some perfect smooth orb. It had mountains, craters, things he called seas. He looked at the Pleiades star cluster.
The Seven Sisters. Subaru, right?
That's the one.
Yeah.
Instead of 7 stars, he saw dozens. Innumerable, he said, that nobody had seen before. It was like the first data visualization, showing things beyond human senses. And Jupiter.
The moons.
Discovered 4 moons orbiting Jupiter, not Earth. That was revolutionary, proof that not everything went around us.
And he realized bigger was better, right, for telescopes?
Oh, immediately. He understood that a larger lens gathered more light and gave sharper views better resolution. And that, right there, is the origin of what astronomers call aperture fever.
Aperture fever.
Yeah, this sort of pernicious disease, as our source expert calls it, of always wanting a bigger telescope. He admits it's plagued him for 40 years, much to his wife's likely consternation.
I bet. But Galileo wasn't always right, was he? Even with his telescope.
No, he was human. He fell into the trap of visual certainty sometimes. He saw mountains on the moon, so they were there. But his theory about tides being caused by Earth's sloshing motion? Wrong. It's mostly the moon's gravity.
And he exaggerated things sometimes.
He did. There's a famous drawing he made of a large moon crater that's quite exaggerated compared to reality. He was using the image, the visual, to make a point, to convey a feeling, maybe even more than just precise data. Images can do that, but they can also mislead if you rely purely on seeing is believing.
That leads to a really interesting point you made earlier about the feeling of discovery.
Yes. This is, I think, one of the most magical things about astronomy. Think about huge discoveries in other fields, the Higgs boson, right?
Yeah.
Or figuring out DNA's double helix structure.
Yeah.
You can read about them, understand them intellectually, but you can't feel what it was like for those scientists at the moment of discovery without, having access to CERN or a high-powered X-ray crystallography lab.
Right, requires massive instruments.
Exactly. But astronomy, it's different. You can pick up a simple, inexpensive telescope, maybe $50 today, one that's actually better than Galileo's best.
They got him in Galileo.
Oh yeah, much clearer optics, probably more stable, and you can point it at the moon, see the craters, point it at Jupiter, see those tiny dots of light, the moons shifting night after night, point it at the Pleiades and see way more than 7 stars.
And feel what he felt.
You could feel exactly that same sense of awe, that moment of personal discovery that Galileo must have felt 400 years ago. It's an incredibly direct, visceral connection to the history of science. And it's accessible to almost anyone, just by looking up.
That's beautiful, actually. A direct line to that foundational moment.
It really is. So wrapping up this deep dive, we've seen how your eyes are these incredible natural telescopes, haven't we?
Yeah, truly amazing capabilities. Single photon detection.
And we've talked about practical ways you can make your vision even better for stargazing, dark adaptation, averted vision, even thinking about your health.
Plus, connecting it all back to Galileo and the ongoing quest for bigger and better views with things like adaptive optics.
It's all part of the same story.
Yeah.
From that first glimpse Galileo had to the giant eyes on the universe we have today.
So the final thought then. If our eyes are literally bits of our brain looking out,
Yeah.
and they can do all these incredible things, detect single photons, adapt, see color instantly, what does that really tell us about the power we already have just built in? And maybe, how much more is out there just waiting for us to learn how to really see it?